Hi, my name is Tony Perro, and this is my semester project for Introduction to Data Science Algorithms. Let's get started. So my project is classification of wine using a chemical factor analysis. This data source was obtained from the UCI Center for Machine Learning and Intelligent Systems machine learning repository. They have a ton of different data sources on there, but I've got links on here. You can go to the site. You can go to the direct link for the data right here as well. So this analysis was performed to integrate exploratory data analysis with models of statistical learning in order to classify wine type. Inferences were drawn from 13 common chemical factors of the three different types of wine, and four different statistical learning models were applied. These four models were logistic regression, k-nearest neighbors, linear discriminant analysis, and quadratic discriminant analysis. So here's just some of the imports that we use, but we can skip by that for now. The file's available so you can take a look at all this yourself as well. So for the data, like I said, we just got some source information here. Loaded up everything into into the Jupyter notebook. Just kind of properly labeled everything here. So you can see there's basically there's wine type, and then there's these 13 different factors. You have alcohol, magnesium content, flavonoids, but just basically kind of the chemical makeup of wine, as well as like some other measures such as like color intensity, hue, etc. And there's 178 samples. And of course, 13 factors there. And not really too much cleaning was needed for this. It was a pretty clean data set off the bat. But I did normalize things, and we'll get into that in a little bit. Here's just some summary stats for each of these factors. Like I said, 178 samples here. The key thing I drew from this was just basically that some of the samples, or some of the factors, some of the data for them were much larger and had much larger variance as well. Like you can see, alkalinity has a value of like 19 and standard deviation of 3. Magnesium 99 and 14, compared to a lot of these are, just over 1 with very small standard deviations. They're very clustered together. And then you have like proline over here is like 746 as well, which is, very large. So we had to try and account for that by normalizing. And so here we just have a few box plots that got pulled up, put together here. And you can see, there's the three types, type 1, type 2, and type 3, and we have 13 different plots here for the 13 different factors. And then for some factors, there's definitely a lot more spread on some of these, and the y values, as I called to attention with the median values, are much larger for certain data points. So I was pretty interested in how that was going to play a role in the analysis. Some of the factors here definitely display collinearity as well. I just drew up a correlation matrix just down here, so you can see, for instance, there's flavonoids and tonal phenols are pretty highly correlated, and then flavonoids with OD, these are also pretty highly correlated with a value of 0.78 there. Really didn't do too much to address this. Didn't really try to do too much with like interaction terms, because I'm not concerned with doing a regression problem. This is a classification problem based on type. But if you're doing a linear regression, trying to work with some of these other points, you definitely have to take this into account. And so, like I had mentioned, we had to normalize the data. So here you can just see, just threw it into sklearn. They have a transform in there. You can just put it into kind of the normal domain. You're just subtracting the mean, dividing by standard deviation, all these data points. So the mean gets centered at 0 and standard deviation gets set to 1 across the board. But it maintains the points are still spread as much as they need to be, so the weight still applies. It just makes things a little bit smoother for the logistic regression and the k-nearest neighbors models. All right, so we can get into the modeling section here. So Like I said, 4 different classification models were used. We did logistic regression, k-nearest neighbors, LDA, QDA. And like I said, with each model, both raw data and normalized data were used. And that was primarily just to see if normalizing the data had an effect on accuracy. Um, and so to get into it, both data sets were split 50-50, just you kind of using the odds evens method that we did in homework 8. So, half the samples were assigned as training data and the other half were assigned as test data. Um, and then, so let's go down to logistic regression here. Um, and so just using the logistic regression model from sklearn, we got an accuracy here of 95.51%. And you can see most of the errors here are happening when type 2 is being classified as either type 1 or as type 3. And there's 2 instances of this for both in either direction on this first logistic regression here. If we go back up to the box plots, you can see that, let's go to the top here, for the type 2 data, a lot of times the distribution is on these factors is a lot larger for whatever reason. So not necessarily for malic acid, but here for alcohol, for ash, for alkalinity, magnesium, you have quite a few outliers. Kind of across the board here, you get, type 2 displays kind of a larger possible range of values. And I think that's a lot of, in a lot of these models, you'll see that that results in type 2 data being misclassified as other types of 1, either type 1 or type 3. So go down here, this is logistic regression on the normalized version of the data, and you can see basically not too much of a difference. It was 96.63, so it just removed one error there. Just one of the type 3 misclassifications was addressed. Then we can go down to k-nearest neighbors, and for k-nearest neighbors I just ran through, I did tested neighborhoods of 1, 2, 3, 4, and 5 nearest points, and then basically just the best fit from those 5 different models was chosen. And so for here, for the raw data, we had accuracy for one neighbor of 73.03%, so it's pretty low. And you can see here I had a lot more issues, misclassifying type 3, which is interesting. But a lot of that gets addressed here with k-nearest neighbors when you normalize the data. And so you can see here on normalized data when this is run, when things are a little bit better tight grouped together, you get a lot less errors. And once again, the errors are kind of focusing on this type 2 misclassifications. Primarily, misclassifying type 2 as type 1. And then we have next the linear discriminant analysis. For this one, kind of the same story that we're getting with the other two, except a bit more accurate, 97.75%. It's actually the best model out of these 4 that I tested. But at the end of the day, it still is running into this issue where it's misclassifying, type 2 as type 1. And that's happening twice in that one. Finally, for the quadratic discriminant analysis, it actually performed a little worse than the linear discriminant analysis. And most of its errors came from misclassifying type 1 as type 2. Which is interesting because it kind of differs a bit from the other 3 models there. Yeah, so to reiterate, so basically, I would say that the LDA model performed the best of the 4 different models that were tested. I had the highest accuracy of 97.75%, and it had the fewest predictions, with only 2 type 2 samples being misclassified as type 1. And so ways to address this, it might be a good move to remove some of the factors, maybe make the model a little bit simpler. If we could figure out which of the factors had the the most important or most relevant to classifying the wines, then we might be able to do a bit better job of dealing with these misclassifications. Also, maybe removing factors that had more outliers, like say color intensity or magnesium content, because I do feel that those outliers are playing a role in those misclassifications that are happening between types 2 and 1. Some other ways to improve these models further would maybe be, performing a stepwise regression, and that way that might be a way of determining which of the factors are most relevant, and maybe settle on 5 or 7 factors rather than using all 13. Um, and this would also make the model much less dimensional, and cut out some maybe unnecessary complexity that's leaving some a bit of confusion there in the models. Another way to improve this would definitely be playing with the training ratios as well. And something I considered was, just playing with the amount of data points that are being sampled. So, maybe you do 5, 10, 15, up to 50% of the samples as training data, and just see how that would perform. So, maybe the model is overtraining or overfitting, or maybe it's underfitting to the data. Oh, but either way, I was pretty satisfied with getting that 97.75% accuracy. I was able to narrow down kind of where the error was coming from, and definitely might take some time here to go back in and see if I can get that accuracy up to 100%. But thanks so much for your time. Hope the rest of your projects went well, and I hope you enjoyed the class as much as I did. Take care. Thank you.